do you see my screen? Yes?
Yes, perfect.
Okay.
Yes, Mohammed.
Hello, everyone. I'm very pleased to be here to give a talk today in this workshop. I'm going to be talking about buoyant injection dynamics of viscoplastic fluids in a confined geometry, which is a work in collaboration with my PhD student, Sohail Akbari. And we would like to thank the sponsors, PTAC, CNRL, NSERC, and Canada Researcher in modeling complex fluids. So the viscoplastic fluid injection have many applications in different areas. But our motivation for this talk comes from the plug and abandonment of oil and gas wells, in particular the dump bailing method. This for which we are looking at the schematic here, if you can see. And in this process, the cement slurry as a viscoplastic fluid is injected into water as a Newtonian fluid, and it sits on a basically a bridge plug here. And this process is done to avoid reservoir fluid migrations to upper levels, prevent contamination of freshwater aquifers, and avoid casing corrosion due to oil and gas leakage. In addition to this process, there are numerous other applications where viscoplastic fluid injections appear, for example, in food processing, additive manufacturing, coating, polymer extrusion, and transport of waxy crude oil in pipelines. So the aim of this talk is to provide an understanding of this basically injection in a sort of fundamental way, and basically provide a view of what's going to happen in the case of viscoplastic fluids. So with that exposure, the outline of my talk is given here, the introduction, and then I will talk about the experimental setup and observations. Then I will move to the theoretical model about the experiment, to explain the experiments, and then results and a brief summary that follows. So in terms of the introduction, areas of interest in fluid injection appear in many scientific domains of fluid mechanics. For example, buoyant flows in pipe and channels. They have been studied in terms of their injection. Buoyant jet injection, mostly for turbulent flows, but also for laminar flows. Injection in porous media, in helical cells, and other relevant areas. There's a large body of work on coranular injection flows. Also, there are works on extrusion, injection, and falling of different materials in air. And another category could be the microfluidic jetting and injection. More relevant to our work, let's talk about viscoplastic extrusion and injection into air. Let's look at the work of Cuso and Gollard, which is now considered to be classical, in which they considered viscoplastic extrusion and dripping. For example, here in this schematic, in this image, you can see that the viscoplastic fluid is injected. It comes down out of a nozzle, and then at some point, it starts to yield, and then it's broken at a given position. They have also looked at the separation lengths versus flow rate for different types of materials. In another relevant work, Barnforth has worked on the modeling of viscoplastic jets with and without inertial terms. An example of the results is given here. For example, by increasing the yield stress, we can see how the unyielded zone and also the pinch-off point is affected. So let's look at our experimental setup and observation. As I said, our motivation comes from plug and abandonment of oil and gas, in particular the dump bailing process. So to be relevant to the process, but in a fundamental sense, we are considering a heavy fluid injected into a light Newtonian fluid, heavy viscoplastic, light Newtonian. We consider a closed end, basically a configuration. We consider the fluids to be miscible, but without mixing. not significantly mixed, and we are considering an injection geometry that is eccentric, similar to the application. So based on this, we have constructed an experimental setup with two eccentric pipes. From the inner pipe, we are injecting, in this direction, we are injecting Carbopol and into water. We have a piston at the end, so we can sort of manipulate the height of the falling. We are using high-speed camera and lighting to be able to basically image this process. The dimensional parameters in our experiments are given here, including the eccentricity, the different radii in the flow, the falling height, the injection flow velocity, the different viscosities and densities, importantly yield stress, and so on and so forth. In terms of the governing dimensionless numbers, based on dimensional analysis, we can obtain several of them, including the Reynolds number, Atwood number, Froude number, Bingham number, viscosity ratio, Peck Lane number, radius ratio, eccentricity, aspect ratio, the power law index of the viscoplastic fluids, and the inclination. So, and also we can also have an important number, which is chi, which is a buoyancy number, which is a combination of Reynolds and Froude number. In our work, we are considering a small density difference, so we are basically neglecting the Atwood number. And as I said, we are considering large Peck Lane number, so we are also removing the Peck Lane number from the parameters. Before I move on to the viscoplastic fluid results, let us briefly look at what happens in the Newtonian case, in which we have identified different flow regions in the flow. As you can see in the spatiotemporal diagram and the corresponding image sequence of the flow. So both fluids are Newtonian. Heavy fluids injected heavy Newtonian injected into light Newtonian fluid, and you will see a lot of mixing. So we have observed a jetting and mixing regime. We have observed a slumping region, and also the point that the front reaches the end. So basically, this is what we have observed in the case of Newtonian fluids. In the case of non-Newtonian fluids, everything changes, as I will explain in this basically slide. So we have, for simplicity, throughout the presentation, we will fix the inclination angle to vertical. And basically, for these movies that I'm going to show, we're going to fix the height, the falling height as well. So we have observed three different flow regimes based on the injection rate. At low injection rate, we have observed the breakup regime. At higher or medium injection rate, we have observed a coiling regime and a buckling regime at a higher injection rate. So I'm going to run the movies. The movies for the breakup and coiling are slowed down, but for the buckling regime, they are sped up so that we can observe what's happening. So this is the breakup regime, in which you can observe that the viscoplastic fluid comes down into the Newtonian fluid, and due to buoyancy, after some lengths, it's basically yields and eventually broken. So this is basically the overall observation in the case of basically low injection rate. At medium injection rate, so the movies are sped up, as I mentioned. The viscoplastic fluid safely reaches the pipe end, and it does not break, and it is so it sits on the end of the pipe and basically starts coiling at a frequency that is more or less constant. And if you increase the injection rate, so the last movie is slowed down significantly, what we can observe is that the viscoplastic fluid exists a nozzle, which is at this point, and then due to the shear stress applied at the interface and the pressure gradient applied at the interface, it starts to sort of buckle, as you can observe in this slowed down movie. And then this buckling continues, and then the flow basically blocks the injected area. So let's look at the basically image sequence of the same movies that I showed, just to have a better view of what's happening. In the breakup regime, so basically we explained what happens in different regimes, but just to repeat, In the breakup regime, the flow, the viscoplastic fluid is yielded and is broken due to the extension. And in the buckling regime, it's basically buckles due to sort of compression. And if neither breakup or buckling occurs, we will have a regime in which the viscoplastic fluid reaches the pipe end and it starts coiling in this manner, as you can observe. So to understand what's happening in these three regimes, and also to be able to provide a sort of a prediction for different types of the regimes, we are basically, we have developed a theoretical model that is an ongoing work and hopefully will be submitted for publication to the Journal of Non-Newtonian Fluid Mechanics after this conference. So the theoretical model is basically considering the schematic that you can look at here. It consists of the 3D eccentric configuration, similar to our experiments, a vertically closed end pipe, heavy viscoplastic fluid, which is basically here coming down, and into light Newtonian fluid. As we said, we are at the limit of high Peckley number. We are using Herschel-Balkley model, for which the equations are given here. And we have a bunch of dimensionless numbers that are given here, including the Reynolds number, the buoyancy number, Bingham number, viscosity ratio, radius ratio, eccentricity, aspect ratio, and power law index. However, in the model, as you will see, the Reynolds number, because we are using a lubrication model, will be also removed. So at the end of the day, we are basically working with 7 dimensionless numbers in our theoretical model. So the equations of motion and continuity and the interface condition in dimensionless forms are given here. We are using, due to the eccentricity of the flow, we are using a bipolar coordinate in which the interface, the core fluid, is represented by basically a Gesai C, which is basically the core fluid interface, and then the walls are by Gesai W. So this is basically where basically the interfaces and the boundary conditions basically are located. We use the small parameter of the system, delta, which is basically the inverse of the dimensionless height of the system, as the small parameter of the system to rescale the parameters and obtain the reduced equations based on a traditional, basically, rescaling of the flow parameters, flow variables, sorry. So the if you assume that delta goes to 0 in a traditional way, in a fixed Reynolds number, we can write down the momentum equations and the continuity equation in this form for both fluids. So K is representing the heavy and light fluid, both of the fluids. And H bar is basically the scale factor for the bipolar coordinate. So in this system, we are basically mapping the flow in the domain of X and Y to a semi-infinite strip in the domain of Gesai and Phi. And the Z is the same. So Z is in the same direction in both coordinates, Cartesian and bipolar coordinate. So we are basically able to use this mapping to be able to solve the equations. Let's analyze the two fluids, core fluid and the annular fluid, in separate equations so that we can better understand what's going on. The Z momentum equation, the momentum in the Z direction for the core fluid is written here, in which basically the term that contains delta and the tau ZZ, basically normal stress, deviatory normal stress, cannot be ignored because the viscoplastic fluid is dominated by compressional and extensional stresses. It's straightforward to write down the normal stress balance condition in which the core annular core fluid is basically used or basically identified by C and the annular fluid by A. If we simply integrate the equations and use the boundary conditions, so we integrate the equations over the thickness of the viscoplastic layer and then integrate it over the length of the viscoplastic layer, we can obtain a simple relation for tau ZZ, which basically relates tau ZZ to the radius of the interface, buoyancy number chi, the shear stress of the annular fluid applied at the interface, and the pressure gradient of the annular fluid applied at the interface. We use the relations of the Herschel-Balke model, and we can simply obtain an equation for the velocity field in the core fluid as well. So now let's move to the annular phase, in which we can write down the equations, and the solution for this, for the stress and for the velocity field, consists of a homogeneous basically solution, a particular solution, which after applying the boundary conditions and considerable algebra, we can obtain analytically for the velocity field, but more importantly for the stress field, which we need for the interface shear stress. So based on our analysis of the basically the flow so far, we have obtained the relation for the yielding lengths versus the Bingham number, the aspect ratio, which is inverse of the height, buoyancy number, the shear stress of the annular fluid at the interface, and the pressure gradient, and also the core fluid basically radius at the nozzle. So looking at this equation, it's easy to see that the yielding, basically, if the denominator is positive, yielding appears due to basically breakup. Sorry, the yielding is due to extension and leads to breakup. And then if the denominator is negative, yielding occurs due to compression and the flow buckles. And the transition between the two cases corresponds to an infinitely long viscoplastic layers for which the denominator is 0. But since the height of the system is finite in our flow, the transition between the two cases can be obtained simply by putting the yielding lengths equal to the height of the system and find the transition between the two regimes. We can also solve for the interface evolution in addition to the threshold that we just obtained for the yielding condition. So we have the zero net flux condition, and we have an equation for the kinematic condition, which we converted to an equation for the flux. We discretize the equation, first order in time, second order in space. We use a traditional basically flux limiter, and then we integrate the equation using the higher order integration scheme. In terms of the results, so we have identified, based on the yielding lengths that I showed, we have identified two groups of dimensionless numbers for regime classifications, including the MH divided by B and chi divided by M. So M viscosity ratio, H was the height, B is the Bingham number, chi buoyancy number, and M is again, yes, viscosity ratio. So here what we can observe is that at large values of this value, we are observing a breakup regime. This is corresponding to large buoyancy, a small viscosity ratio, and a small basically injection rate. On the other hand, at small values of chi over M, we are looking at the buckling regime. So these lines are coming from the model, obviously. So we are observing the buckling regime. This corresponds to a small buoyancy number, small density difference, large viscosity ratio, and a large injection rate. And then the transition between the two can be obtained just the region between the two regimes. Here in this figure, we are looking at the non-monotonic variation of the regime transition versus the radius of the inner fluid. But what we can say in general is that if the radius of the inner fluid is large, the area for which the buckling regime occurs expands. I can go through this in the discussion session if you would like, or in the question. So in terms of the regime classification.
Just 1 minute.
Sorry?
So I was just saying about a minute.
Yes, sure. I will try. Yeah, so regime classification, we did numerics experiments, and we have a good comparison between experiments and the model, except for some regions where due to inertia or other effects that I can explain in the discussion session or in the question, why we have some discrepancy. But overall, it's the comparison in terms of the regime is good. We are also looking at the interface evolution for, if you give me 30 seconds more, we can look at the interface, basically shape, and then superimpose on the interface shape the value of the tau ZZ of the core fluid, and we are here we have no annular fluid. So we are looking at how the stress is concentrated at the necking point. But if you consider the annular fluid, we see that things are slowed down in terms of the breakup. And then we are looking at here, for example, no annular flow is still looking at the sort of yielding and breakup for a different set of parameters. But here, so with respect to the two basic cases, the viscosity ratio is increased. So we are looking at this sort of buckling, as you can see in this case. And then the last slide is we can look at the different scenarios for either yielding or buckling, or we can try to superimpose the velocity field onto the basically necking point and see how basically necking or buckling is affected by the annular fluid. So with that, I just go to the summary and leave this slide for the question, and thank you for your attention.
Thank you, Mohammed. I think I've got a couple of questions by the usual suspects, Ian and Madi, but I'd like to ask a question, if that's okay. So why did you start with all the experiments you've shown are for an eccentricity, it was not centered, right?
Right.
So is there a reason why you started with this case? Is it a particular relevant case or?
Yes, because in most cases in the, our motivation comes from plug and abandonment of oil and gas wells, in which basically always, because they are putting a pipe inside the casing, the inner pipe always slides to one side, and then they can have a sort of a slight inclination. So you always have one inner pipe laying on the outer pipe. So this configuration is more relevant to the application of the dump bailing method in plug and abandonment that I mentioned. But as a future work, as a next step, we are looking at the configuration of the eccentric. Of course, eccentric equations are much simpler to, centric equations and centric experiments are much simpler to solve.
Thank you. Ian, do you want to ask?
Sure. Yeah. Well, it's very nice, Mohammed. I like the. I don't think I'd seen that before. So the breakup and all that. It's very nice to get the domains, the regimes all predicted. Yeah, I was just wondering whether you could even just throw away the annular phase stresses, because it's basically water, isn't it? And so but I think at the end you showed that maybe wasn't possible. But
yes, so you cannot obtain. Do you still see my screen?
Yeah.
Yeah. So this is with no annular flow, right? So you're gonna always have basically breakup at some lengths, right? Because of the buoyancy. But you need the stresses from the annular fluid so that you can sort of apply it at the interface so that it can move the interface up so that you can have the buckling. So buckling occurs because of the applied sort of shear stress at the interface by the annular fluid, and also the pressure gradient that is created by the zero net flux condition. So you cannot throw out the annular flow.
Okay, yeah. So with only buoyancy, it
won't break up. Yeah. So you need the basic annular phase to have the buckling.
Okay, thank you.
You're welcome.
Thank you very much. So I think, thank you again, Mohammed, and I think we'll move on and keep the rest for the discussion later on, if that's okay.
Sure.
The next talk.
I can